Video I am going to talk about the binomial distribution, and the binomial distribution is a special case of our general probability distributions. Alright. Now, a binomial distribution follows certain basic properties, right? And those properties are listed right here. Right? You have to have a fixed number of trials. Right? That means your experiment is performed a finite number of times. Right? And if it's repeated, it's always repeated that many times. The trials have to be independent of one another, so each time you perform the experiment does not affect the next time you perform the experiment. Only two outcomes. All right, binomial, right, by two, only two outcomes. You have a success or you have a failure. Right, and that's it. The probability of success is the same for each trial. Okay, and also just to mention, success and failure have to be disjoint. There's no overlap between success and failure. Now, when you do a binomial experiment, the notation we're going to use is standardized. So we use n for the number of trials. We use p, lowercase p, for the probability of success, and then q, which is 1 minus p, for the probability of failure, and x represents the number of successes. All right, now you calculate the binomial probability, p of x, this way. N cx, right, that's the combination of n things taken x at a time, p to the x times 1 minus p to the n minus x. Right? So that's our basic setup. So the first thing I want to do is look at some binomial experiments, right, or possible binomial experiments. All right, so I want to look at these three situations, determine which of the following probability experiments qualify as a binomial experiment. For those that are binomial experiments, we're going to identify the number of trials, the probability of success, the probability of failure, and the possible values of the random variable x. All right. So let's start with the first one. Okay, so we have an experiment in which a basketball player who historically makes 80% of his free throws is asked to shoot 3 free throws, and the number of free throws made is recorded. All right, so we need to check our properties. Is there a fixed number of trials? Well, he's making 3 free throws. All right, so there's a fixed number of trials. That means for this experiment, n, oh, no, it doesn't. For this experiment, n equals 3. And why isn't my pen writing? I know why my pen's not writing. Sorry. Okay, let's try that again. N equals 3. Okay. The trials are independent. Well, we're going to assume that making one throw or not making one throw is not going to affect the next time he makes a throw. All right, so they're independent. There's only two outcomes, success and failure. Okay, well, if he makes a free throw, then he succeeds, and if he doesn't make a free throw, then he fails. And there's no overlap. You can't sort of make a free throw. All right, so that's satisfied. And then the last one, the probability of success is the same for every trial. And the probability of success in this case is given to us right here. All right, historically he makes 80% of his throws, so that means the probability of success p is 80%, or 0.8. So to fill out the rest of this here, the probability of failure, right, 1 minus p would be 1 minus 0.8, or 0.2. And then what are the possible values for x? Well, he could make no free throws, he could make 1, he could make 2, or he could make 3 out of his 3 tries. Okay? All right, so let's look at the next one. All right, the number of people with blood type O negative based on a simple random sample of size 10 is recorded. According to the American Red Cross, 7% of people in the United States have blood type O negative. Alright, so let's look at this. Alright, fixed number of trials. Yes, we're taking a random sample of 10, so our number of trials is 10. Alright, the trials are independent. Well, it's a random sample. Alright, and we have 10 different people, so the trials are independent. Only 2 outcomes, success or failure. Well, we're interested in people with O negative blood type, so succeeding is finding someone with O negative blood type. Failing is finding someone that does not have O negative blood type. Alright, so there's only 2 outcomes. The probability of success is the same on every outcome. Well, the probability of having O negative blood is 7%. Alright, so my P here is 0.07, right, 7%, which makes my 1 minus P 1 minus 0.07, which is 0.93. And then the possibilities for X, right, I could have no one in the sample be O negative. I could have 1 person in the sample be O negative. I could have 2 people in the sample be O negative, all the way up to all 10 of them being O negative. Okay, so that is definitely a binomial experiment. How about this last one, a probability experiment in which 3 cards are drawn from a deck without replacement and the number of aces are recorded. All right, let's go through the list. Fixed number of trials. Yes, we're drawing 3 cards. All right, the trials are independent. Let's take a look at this here. We're drawing 3 cards from a deck, one after the other, but we're not replacing them. All right, so think back to your probability here. If I draw 1 card from the deck, all right, we're recording, what are we recording? The number of aces. All right, so what's the probability of drawing 1 ace from a deck of cards? All right, is 1 out of 52. Now, if I don't replace that second card, what's the probability? If I don't replace that first card, what's the probability that I draw an ace on the second card? All right, well, I've reduced my number of aces by 1, so now I'm down to 3, and I've reduced my cards to 51. All right, now these two are not the same. All right, so these trials are not independent. Alright, so this last one here is not a binomial experiment. So this one we get to X this one out here. That is not a binomial experiment. Alright, so whenever you see a problem, you always want to check those conditions to make sure that you actually have a binomial experiment. Okay. Alright, so now let's look at another problem here. It's on problem 2. Okay. So let's go back to our Red Cross problem here. Okay, so again, according to the American Red Cross, 7% of people in the United States have blood type O negative. A simple random sample of size 4 is obtained, and the number of people, X, with blood type O negative is recorded. Construct a probability distribution for this random sample. So we've talked about probability distributions before. Alright, so I've done our setup here, right? Let's pick out all of our relevant information. Alright, so you have a sample of size 4 right there. That's important. We have the percentage of people in the United States that have the blood type is important. Okay, so our sample size is 4, so that means we have the possibility here of 0, 1, 2, 3, or 4 for our X. All right, our probability of success is 7% or 0.07. All right, so what I get here is N equals 4 and X, I'm sorry, not X, P equals 0.07. So I can start to fill in my formula here. I know the N and I know the P. So let's write out a general formula for this particular problem. All right, P of x is going to be n is 4 p x times p to the x times 1 minus 0.07 to the 4 minus x. Okay. All right, so now I can, let's keep in mind this 1 minus 0.07 here is really 0.93, so I'll just mention that right there. Okay. So let's start looking at these. All right, P of 0. What is that going to be? That's going to be 4. And I said P here, and I meant C. Why did I say P there? Because I do things like that. All right, C, 0. 0.07 to the 0 times 0.93 to the 4 minus 0. Right. Now you can work this out on your calculator. All right, it's easy enough to do. We can take a quick look here if you want, just to remind you where all the functions are. All right, so the combination is in the math menu. And now my calculator's going to fail. Okay, never mind. I'm going to put that up in a separate video. All right, I'll put that up in a separate video. All right, so you're going to calculate 4C0, multiply that by this, multiply that by this, and you will end up with 0.7481. Yes, 7481. All right, so my first probability here is that. All right, so all we need to do to fill out the probability distribution is to calculate each one of these for C1, 0.07 to the 1, 0.93 to the 4 minus 1, so that's 3. Right, and we do that when we get 0.2252. Alright, so my next one here. I'm going to fit one more down here. P of 2. 4C2. 0.7 to the 2. 0.93 to the 4 minus 2. And if you work that one out on your calculator, you will get 0.0254. Alright, so that's our next one. Alright, P of 3. Alright, so we get 4C3. And then 0.07 to the 3, 0.93 to the 4 minus 3, and that ends up being 0.0012. And then the last one, P of 4, which is 4C4, 0.07 to the 4, 0.93 to the 4 minus 4, and that ends up being 0.0001. 0.0001. Okay. All right, so again, all of those can be carried out on your calculator easily enough. All right. Okay, so let's look at, now before I go on to what I want to go on to next, which is going to involve looking at some word problems, I just want to remind you of some language from algebra. Okay, right here. All right. When you see the words at least or no less than, we're talking about greater than or equal to. When you see more than or greater than, we're talking about greater than. Fewer than, less than, no more than, or at most, less than or equal to, exactly, equals, or is equal to. All right. Okay, so let's look at a problem here. All right. According to the CTIA, which is the Cable Television Institute of America, in case you are interested, 25% of all U.S. households are wireless-only households, no landlines for their phone. In a random sample of 20 households, what is the probability that, and then there are a few there. Now, I'm going to set these up. I'm not going to work them out yet. I'm just going to set them up. All right, so let's pick out a few things here. All right, 25% of all households are wireless only. All right, that's my P, 0.25. All right, we're taking a sample of 20 households, so that's my N. Now the X's we're going to get from the questions here. All right, so let's look at the first one. All right, for A, the probability of exactly 5 being wireless only. All right, so we're looking for the probability that X equals 5, exactly 5. All right, and that is just a one formula solve. For B, fewer than 3 are wireless only. All right, so that means X is fewer than 3 means less than 3, not including 3. All right, so what am I going to do to figure that out? Well, I have to calculate the probability of each of those values that are less than 3, right? Probability of 0 plus the probability of 1 plus the probability of 2. Okay, so this one, all right, I guess I should make the notation change over here. This is just the probability of 5 by itself. All right, C. At least 3 are wireless. So at least means 3 or more. So 3 or more, that's the probability that X is greater than or equal to 3. All right, all the way up to 20. All right, so I'm not going to write all of them down, but so you would start with 3, P of 4, plus P of 5, and you would have to do this all the way up to P of 20. All right. Now, there's one thing you can do, right? Because you're not going to want to have to calculate all of these by hand at all. And even with the shortcut methods I'm about to show you, you can use the complement. Look back at your probability lesson and you'll see we talked about the complement of a probability. Alright, so if I'm looking at 3 through 20, then the complement would be 0 through 2. Right? So I could look at this as 1 minus the probability that X is less than 3, which is going to be a little bit easier to calculate. Right? And then the last one here, D, the number of households that are wireless only is between 5 and 7 inclusive. Alright, so that means that X is greater than or equal to 5 and less than or equal to 7. Alright, so what do we need here? We just need P of 5 plus P of 6 plus P of 7. Okay. Alright, now I'm going to see if I can get my calculator working here again. And if I can get my calculator working here again, then we can actually make this work. Let's see. Yes, okay, so here's my calculator. So let me come over here. Alright, so we're going to clear this. So if I'm going to do, let's just say P of 5. Right, so P of 5, I need, for P of 5, what do I need? I need N, which is 20, Cx, which is 5, P to the x, and 1 minus P, which would be 0.75, to the N minus x, so that would be 15. Alright, so let's see if I can make this work now. Yes, I have a blinking cursor. That's good. Let's get this in the frame. Alright, so we do 20. And then remember the combination is math, probability, whoop, that's P, combination, pull that up, and that is 5. Alright, so that is 15,504. Alright, so now we want to take that and multiply it by 0.25 to the 5th times 0.75 to the 15th and hit enter. Alright, so 2023. Alright, so 2023 would be my probability here. 2023. Right. Now, do I want to have to do that even if I have 3 of them? Or even worse, if I have 17 of them? Alright, no I don't. In fact, I really don't. Alright, so we have another way of doing these calculations, and that is actually by using a table. Now, I have a binomial table here. This is similar to the one that's in the back of the book. Alright, the binomial table in the back of the book is on page A3. I couldn't get that one to fit on the screen properly, so I'm going to just take this one that I found online. Alright, so if I come all the way back to the beginning of the table here, alright, you'll see, now they use R for the number of trials where we're using X, so technically right here, this would be X. Okay? So the table is broken down into blocks. The blocks are defined by the number of trials. Alright, so 2 trials, 3 trials, 4 trials, 5 trials, and so on. The probability of success and representative examples are right here. Alright, so keep in mind problems have to fit into those particular probabilities. And then the number of successes along here. Okay, so the way you work this table is you first look for your n. So suppose I had 5 trials, so here's n equals 5. Alright, so I'm only interested in what's going on in this block right here. If the probability of success on any one trial was, let's say, 20%, then I'd be interested in this column right here. And then you would simply line up 1, 2, 3, 4 like that. Alright, so I want to look at, very specifically, I want to look at something that's going to be a little more towards this problem here. So what I did was I took out one little part of the binomial table here for our problem. So we have 20 trials, and our probability of success is 0.25. So where I'm interested in for answering these questions is just this table here. Now this table only goes to 3 decimal places. The table in our book goes to 4. It's not really relevant. The method is the same. Alright, so if I want to know about 5 trials right here, where am I looking? Well, I'm looking right here in 0.202, is what that table says. And if you come back to right here, okay, 202 to 3 decimal places is what we got. So now if I want to do any of these other ones here where I'm adding up a bunch, all I have to do is come over to my table and say, well, if I want less than 3, all right, what am I going to do? I'm going to look at less than 3. So I would be adding up 0, 1, and 2. And I would add those up and I would have my answer. If I wanted 3 or more, well, then I'd be adding up everything from here down. All right, even though the last few are 0. Okay. All right, so that's how the binomial tables work, and you can find the tables in our textbook. Now, for those of you who have the TI calculators, the TI-83 calculators here, there's one more thing that can speed things up for you, and that is the 83 and 84 calculators will actually calculate with a function the binomial probabilities. And you get to that right up here. See where it says DSTR above variables? All right, so if I go second DSTR, come on, second okay, now it's frozen again. All right, sorry. I'll put that up in a separate video. Okay, so let's move on. And we'll move on to what we can do in terms of determining the mean and standard deviation, right? If you have a probability distribution, you can calculate its mean and standard deviation. All right, so for the binomial distribution, the formula for the mean is just n times p. And the formula for the standard deviation is the square root of n times p times 1 minus p. No tables, nothing fancy. It really is just those formulas. Now, when you look at a binomial distribution, all right, it turns out if the condition that the variance n times p times 1 minus p is greater than or equal to 10 is true, then the distribution is bell-shaped. So remember, with a bell-shaped distribution, we have the empirical rule, right? The empirical rule. What the empirical rule said in particular is that about 95% of the data will fall within 2 standard deviations of the mean. All right, this gives us a good test for outliers, for unusual results. So if we look at this next problem here, all right, according to, again, the Cable Television Institute of America, 25% of all households are wireless only. In a simple random sample of 300 households, 92 were wireless only. And the question is this an unusual result? All right, so I need to do a couple of things. I need to calculate the mean, and I need to calculate the standard deviation and the variance. Okay. So if I do this here, I need n, right? What is n? The number of trials. The number of trials is our sample size, which is 300. I need the probability of success on any one trial, which, again, we've already said is 25%. So 0.25 equals 0.25. And then I need my x, right? My x is 92, or wireless only. Okay. So let's see what we have here. The mean is n times p, right? Which is 300 times 0.25. 300 times 0.25 is 75. Right? The standard deviation is the square root of n times p times 1 minus p. So that's going to be the square root of 300 times 0.25 times 1 minus 0.25, which is the square root of 56.25. Right, which is, if we take the square root of that, 7.5, roughly. Okay. All right, so we have our mean, we have our standard deviation, and I did calculate the variance here, right? N times P times 1 minus P is 56.25, which is greater than 10, greater than or equal to 10, which means I have a bell-shaped distribution. All right, so let's see where our x value of 92 falls within that bell-shaped distribution. All right, I'm interested in 2 standard deviations. If I'm more than 2 standard deviations from the mean, then it's going to be considered an unusual value. All right, so let's get that interval. All right, so if I do the mean minus 2 standard deviations, that's going to be 75 minus 2.75, 2 times 7.5, sorry, which is going to be 60. And if I do the mean plus 2 standard deviations, 75 plus 2 times 7.5, that is going to be 90. All right, so what that means is, on a number line, right, if my mean is 75, then between 60 and 90, I'm going to have 95% of my data. All right, so what happens with that 92? Well, that 92 falls out here. All right, so if 92 falls out there, 92 is above 95% of the data. Okay, because it's above 95% of the data, we'd call this an unusual value. All right, this is definitely an unusual result. Now, the unusual result is probably due to the sampling, right? You could sample if you sample in Silicon Valley, all right, you're certainly going to end up with a lot more households with wireless-only connections. Okay, so the unusualness is due to the probably due to the sampling. All right, so what you can do now is if you go into your textbooks, you can take a look at some homework problems. All right, so go to page 320 and take a look at problems 7 to 49. All right, you can look at the odd ones. The answers are in the back of the book. And when we get to class, I will take any questions that you have. Okay?